Hello everyone. This lecture is about the solution of partial differential equations. In particular, we will focus on the solution of the diffusion equation. So last week, we have made progress with numerical modeling and we've learned how to solve an ordinary differential equation. So remember, the ordinary differential equation basically has a quantity which evolves, for example, n here, and inside the same expression you have n as well as the derivatives of n along one axis. So here it would be time. The direction would be time. The example we studied was the radioactive decay, and we made examples of single and chain decays. So this week we will move towards partial differential equations. Just as a memory of last week's lecture, what is a model? You should remember that a model is not the real world, but it's merely a human construct to help us better understand real world systems. So what we're going to study today is not the reality, but we are trying to get close to it with modeling. So the basic principle here is that there are key features in the common that are common to the development of any model. And what we discussed last week was the fact that we need simplifying assumptions to design a model. We also need initial conditions. They must be identified and selected. They must be thoughtfully selected. In the case of partial differential equations, we also need boundary conditions. So boundary conditions will be basically data that we want to set to control the value, for example, of a function or the value of a quantity on the sides of a model. So for example, if you look at the temperature evolution inside the room, the boundary condition could be the temperature of the wall or the heat flow through the room, through the windows, something like this. And the third point, remember, is that the range of applicability of the model should be understood. So we should understand what the model can do and to which extent it can be used. So again, I paint this in red. The boundary conditions, it's really something that is necessary for the solution of the partial differential equation here. So the focus of today is the diffusion equation. And the diffusion equation looks like this. On one side, you have dx dt, so you have the rate of change of a quantity. And this is equal to kappa dx2 d small x square. So that's the second derivative in space of the quantity x, or the field that represents the quantity x. So t is time and x is space. We have two dimensions along which we take the derivative of a function. That's really a partial differential equation. So for the general knowledge, the diffusion equation is a so-called parabolic equation. There exist other types of partial differential equation, namely hyperbolic or elliptic equations, and these are not addressed in this course. These are addressed in advanced courses of modeling. So let's have a look again at this equation. We have the first derivative in time, and this is why we're going to need initial condition. To compute the rate of a quantity, we need to know where we started from. This is the same as for the ordinary differential equation. To compute the evolution of a quantity of a radionuclide, we needed to know how much of it we had initially. So here it's the same. We're going to monitor the temperature, for example. We will need to know where we start from. what was the temperature at day 1. In the right-hand side, you have the second order derivative in space. And to evaluate this term, we will need boundary conditions. So the question you may ask is, does this matter at all for earth sciences? Why do we study this equation? And the answer is, of course, yes, it matters, and not only a little, it matters a lot. Diffusion is everywhere from the large scale. So here would be an example of an intrusion, a magnetic intrusion that enters into a country rock, and that will trigger metamorphism by diffusing the diffusion of heat inside the country rock. It matters the scale of the topography. So if you have a mountain that is rough over the years due to erosion, it will smoothen out. And how to model this process of smoothing the topography and decreasing of topography, this can be done by modeling the diffusion of hill slopes. Any kind of solution, so that's even beyond earth sciences, but if you put a sugar in the water, and then you can study how the sugar is going to dissolve, to spread inside your glass of water, this is also a diffusion problem. If you're doing a geochronology, you want to understand the diffusion of lead in a zircon. That's, of course, a diffusion problem. Another interesting problem is for geomechanics. If you want to study why Pisa's tower is dipping in one direction, one needs to understand how the fluid pressure in the soil is being distributed and modified by the surface loading imposed by the Pisa tower. So there are diffusion problems everywhere in earth sciences, and it's a good thing to learn about modeling the diffusion equation. So let's focus on the application of diffusion to heat. So what we're going to do, we will study, it's the same equation as before, except that x has been substituted by t, and t is a field that represents the temperature. Again, we have derivatives with regard to several dimensions, time and x, and we seek a solution of t through time and space. We will need to integrate the equation. So, and these PDEs, this partial differential equation, they can be used to model diffusion, advection, waves. These are the other types of equations I was mentioning before, and they are used also beyond earth sciences. They are used in biology, risk, physics. So you can apply the knowledge you learn in this lecture to a lot of different fields and problems. So the heat diffusion, maybe you want to think about it a bit. Heat diffusion, for example, you hold a metal bar away from a flame. So you have it in your fingers here, and on the other side, you have a flame that's burning, a candle, and that's transferring heat into the metal rod. This is heating up, but you will not feel the heat instantaneously. It will take time because diffusion takes time. This is a process. The heat is being diffused inside the bar, and it will take time until you feel the heat at your fingers. And eventually it will become hot, but will not be as hot as holding it from that side. So the process of diffusion will allow you, for example, to model this basic example. So here we have one physical parameter, K, and that's what we will call the heat diffusivity. It's in meters squared per second. One time derivative. So it's the rate of temperature, so it will be Kelvin per second. And a second order spatial derivative. This will be a unit Kelvin per meter square. So let's go in the details of a simple numerical solution of this equation. So here's our prototype equation right there. And the question is how to handle partial derivatives. You should not be too afraid about partial derivatives because we have been solving problems involving partial derivative for already 4 lectures. So we started with partial derivative when we are computing the slopes on the digital elevation model, and we use partial derivative in the previous lecture to model the rate of change of a quantity of radionuclide. So let's represent our data with this diagram. We will have the time axis to be a vertical axis. And here we have a x. This is the space axis. So we consider 1 dimension for the diffusion. We have an index I running from 1 to nx. So I is an index that represents the different cells in space, the different cells of the model, first cell, last cell. N is a time index. So n will be n equal 1 will represent the initial state of the model, n equal 2 represents the second stage, and it will run until nt, for example, the number of time steps in your model. The size of each cell of the model in space is delta x. So that's a width. It will be in unit length. The spacing between 2 time increments is delta t. So to represent the state of the model through different time slices and in space, you will have a spatial resolution and a temporal resolution, delta x and delta t. So this is a discretization of both space and time. Now, let's think about one index I and one index n. So we know the temperature T at index n, this is the current time, and at a position I. So we have a neighbor to the right. It's T at the same time index n, but this is index I plus 1. To the left, the neighbor here is T at time index n, space index I minus 1. If we go in the future by an increment of delta t, we have T index n plus 1, comma I, and the two neighbors are I plus 1 and I minus 1. So let's first consider this side of the equation. That's the rate of temperature. So the time derivative dt dt, we will simply approximate it by a finite difference, an increment of temperature divided by an increment of time. So how to formulate the increment of temperature? It will be T n plus 1, comma I minus T n, comma I. This temperature minus this temperature is the difference of temperature between these 2 points in time. And of course, this is scaled by delta t, which is here a model parameter. It is the spatial resolution. Now, let's look at the right-hand side, and in particular at the second order derivative. So now, Second derivative we haven't touched yet. But there's no reason to be afraid of it. So let's dissect it. We will approximate the second order derivative as the derivative of a derivative. So we know how to compute dt dx, and to this dt dx we will compute the difference of dt dx scaled by delta x. So we will apply a difference to something which is already a difference. We take the derivative twice. So this may sound a bit fancy, but it's simple to apply. Let's do it on this example here. So no worries. Let's compute the first derivative in space. So with regard to Tn, I, we can take the right value to compute the derivative between these 2 points. So we take Tn, I plus 1 minus Tn, I, and we scale it by delta x. This gives an approximation of dt dx evaluated in between those 2 points. So on this face here, at this coordinate, we have this first derivative. There is also another derivative which is living on the other side here, and this is dt dx evaluated at this position. To compute this one, we will need to take Tn, I, and we subtract Tn, I minus 1. Scale it by delta x again. So now we have two first order derivatives which are approximated on each side of one cell. What is left to be done is to compute the second order derivative, which is nothing else than the derivative of the first derivative. So if you know this one and you know this one, both of them were easy to compute. You can also know that one because it's the difference between this one and this one divided by delta x. So let's do it. We have this expression, 1 over delta x, times the difference between two approximations of the first order derivative. So to evaluate this as a function of the temperature, you have to substitute the value of the first derivative to get an expression as a function of Tn I minus 1, Tn I, and Tn I plus 1. So you just have to substitute the definition of the first order derivative inside this expression. The result is this. Simply that the second order derivative can be approximated by 1 over delta x squared times Tni plus 1 plus Tni minus 1 minus 2 Tni. That would be the expression to construct in order to evaluate this term and approximate this term. So we have our prototype equation here, and we have the discretized equation right below. The rate is discretized by this expression, so we have a change in time index. And the curvature here, the second order derivative, is computed this way. We have 1 over dx, Tni plus 1 plus Tni minus 1 minus 2 Tni. To solve for the new value of temperature at point I, we will need to solve, to basically isolate T and I in the left-hand side. So now let's solve for T and I plus 1, comma I. So we basically multiply everything by delta T and get this term to the right-hand side. There you go. You have a final update of temperature. That's how it looks. T and I plus 1 is equal to T and I plus kappa delta T over delta x squared times T and I plus 1 plus T and I minus 1 minus 2 T and I. That's for the update of the temperature. So we have derived here an explicit finite difference scheme for integrating the heat diffusion equation. So in other words, we are now able to solve for the spatial distribution of T as well as its temporal variation. So that's cool. With this expression, we can solve for this. Of course, there are some warnings. So now the first warning is that we need initial condition to initiate the computation. So we will need to set the value of temperature at time n in order to compute time n plus 1. So to compute this thing, we need to know that, all the temperature at time index n. So we will need to know the distribution in space at the previous time increment. So that applies to the very first time step. We need to know this value. Second warning is that we need boundary conditions. We have space index I plus 1 and space index I minus 1. So if we are sitting on a node of position I, we need to be able to access information at I plus 1. So access the neighbor to the right, and to access information at I minus 1, which is the neighbor to the left. If you're sitting on the left side, it's difficult to go out to the left. So we need to apply a boundary condition. Same if you're on the right side. If you have no neighbor on the right side and you are asked to access information from the neighbor to the right side, you need to do something specific, which is applying a boundary condition. The third warning is that the method we used here has a limited range of stability, and the maximum time step here should be limited by this criteria. So delta T has to be smaller or equal to delta x squared divided by 2 kappa. That's the limit for stability, and it's something we study in more in advanced lecture also. You can try to play with delta T and you will see that if you go above this criteria, it will blow up. So be aware, make sure you remain below this level. So in the practice, what we're going to do, we are going to study the cooling of a dike. So we will model the thermal relaxation that occurs right after an intrusion has intruded into a country rock. So we will start and we will have an initial temperature profile that will be the initial condition. And we will study how the temperature or the heat is going to diffuse inside the country rock and how the temperature of the country rock is going to evolve in response to intrusion of a dike. So these will be the details of the model, the initial condition, and we will go step by step during the exercise session to solve the questions which are being asked. So you will have to implement the formula we derived during the lecture, and by using this formula you will be able to model the thermal relaxation of the dike and the heating up of the country rock. So In this session, we learn how to solve a partial differential equation, namely the diffusion equation here. And we've learned how to discretize this equation with an explicit finite difference scheme, and we studied the thermal relaxation of around a cooling dike. So that's the summary for the modeling lecture. The models can be used to study natural system. They are predictive because with a model you can predict what will happen over time, and they are reproducible. That's a big thing about the modeling. And these models are based on ODEs and PDEs. And we've learned very basic solution method for tackling problems which are governed by ordinary differential equation, like the radioactive decay case, and partial differential equation, like the heat diffusion case. So thanks a lot for your attention.